Understanding our climate has never been more important. The key to understanding what's going on is to model the complex reactions taking place between the gases in our atmosphere. Bringing together stoichiometry and gas laws is step number 1. This is Real Chem. I'm going to show you an approach that can be used to visualize the steps to calculate gas volumes in atmospheric reactions. Now, this is just a way that works for me, but you can find an approach that feels right for you. Let's explore. Dichloro-difluoromethane is a chlorofluorocarbon, or CFC, which can be recycled into different gaseous compounds by reacting with hydrogen to produce difluoromethane, which is a compound useful in chemical manufacturing and in refrigeration. Our challenge is to find what volume of hydrogen at 225 atmosphere and 35.5 degrees Celsius will be required to react with 1 ton of dichloro-difluoromethane. Let's take a look at a roadmap for our calculation and then pick a route to get our answer. So notice there is a side for compound A and a side for compound B. A is the chemical that we have information about. In this case, the dichloro-difluoromethane. Compound B is the chemical that we are trying to work something out for, and in this case, the hydrogen gas. See how the two sides are linked in the middle between the two mole boxes? This is because the amounts of dichloro-difluoromethane and hydrogen gas are related to each other through the chemical reaction which occurs between particles. From the balanced chemical reaction, we see that for every molecule of dichloro-difluoromethane that is consumed, 2 molecules of hydrogen gas are consumed. Or equivalently, for every mole of dichloro-difluoromethane that is consumed, 2 moles of hydrogen gas is consumed. This ratio of 1 mole of dichloro-difluoromethane over 2 moles of hydrogen gas is called a stoichiometric factor, and it comes from the coefficients in the balanced chemical reaction equation. The stoichiometric factor lies in the middle because it connects the amount of one compound, the dichloro-difluoromethane, to the amount of hydrogen gas. The remaining connections stay within a certain compound and convert between different ways to express the amount of that compound. Now, identify your starting point and your endpoint on the roadmap. We're told that we have 1 ton, which is a mass, of dichloro-difluoromethane. So we're going to start on this side in the box labeled mass. We're trying to find out the volume of hydrogen, that is the volume of a gas. So our endpoint on the B side is the box labeled gas. Next, we trace the path from the gram box on the A side to the gas box on the B side and remove all unused components to isolate this path clearly. So let's follow the path. We start with 1 metric ton of dichloro-difluoromethane, which we need to convert to grams. Now that we have this mass in grams, we can begin the calculation. Step 1 of the path is to convert our grams of dichloro-difluoromethane to moles of dichloro-difluoromethane using the equation of grams equal to moles times molecular mass. Remember to calculate the molecular mass by adding up all of the atomic masses in the formula of dichloro-difluoromethane. We find that we have 8,264.5 moles of dichloro-difluoromethane. Now, step 2 of the path converts the moles of dichloro-difluoromethane to moles of hydrogen. Using the balanced equation of the reaction, we can see there needs to be 2 moles of hydrogen to every 1 mole of dichloro-difluoromethane. So however many moles of dichloro-difluoromethane you have, you need to double it to work out your moles of hydrogen. This gives us 16,529 moles of hydrogen. Now, step 3 of the path converts your newly calculated moles of hydrogen to a volume of hydrogen gas. And to do this, we use the ideal gas law, which is PV equals nRT. We were told the pressure is 225 atmosphere. As this pressure is in atmosphere, remember to use the correct value of R in the equation. The temperature was given as 35.5 degrees Celsius. In chemistry, we always convert temperature to Kelvin by adding 273. So the temperature becomes 308.5 Kelvin. N is the number of moles of hydrogen that you have just worked out. So plug all the numbers in, rearrange the equation, and you have just worked out the volume of hydrogen gas required, which is 1,861 liters. This seems complex. It is complex at first, but taking it step by step helps. Practice it, and it will become increasingly straightforward. One day, you might be using this approach to help fix our atmosphere, so it will be worth your efforts. So explore and remember to have fun.